Hello everybody. This presentation is based on the paper Algebraic Synthesis of Fibonacci Switched Capacitor Converters. The paper is authored by Alexander Kushnerov and Professor Ben-Yaakov. Switched capacitor converters use a number of switches to commutate so-called flying capacitors. In this simplest example, the flying capacitor C is charged by the input voltage source and then is connected in series with it and discharged to the load. Under no load condition, the output steady-state voltage will be twice the input voltage. The operation of this converter does not differ in principle from the operation of charge pump. However, the charge pumps use clocks, and not switches, and normally operate in open loop, meaning there is no regulation. Any switched capacitor converter can be represented by a simple equivalent circuit that includes a target voltage source and serial resistor. This resistor is called equivalent resistor and represents the conduction losses in the converter. Connecting the load to the equivalent circuit, we actually get a voltage divider. Consequently, the converter efficiency can be expressed as the ratio of the output and target voltages, or that is the same as the ratio of the corresponding resistors. It's evident thus, that to obtain high efficiency the target voltage must be very close to the output voltage. This can be achieved by keeping R equivalent as small as possible and adjusting M as required. However, adjustment of M poses a difficult problem since M depends on the SCC topologies. Let's consider the SCC with the target voltage equal to 2/3 of V in. The output voltage of the converter is kept at 2 volt by adjusting the equivalent resistor. The converter starts to operate when the input voltage is equal to 3 volt. At this point, the output voltage is practically equal to the target voltage, and therefore the efficiency is maximal. As the input voltage increases, the output voltage will increase also, and to keep it constant one needs to increase the equivalent resistor. This implies increasing the losses, which leads to lower efficiency. The total efficiency can be improved if SCC has many target voltages. An effective way to accomplish this is the binary SCC developed in the previous study. For n flying capacitors, the number of target voltages in this SCC was increased to be to the power of n-1. By this, the total efficiency was improved as shown in this figure. The objective of this study was to introduce additional target voltages to the binary SCC without adding capacitors or switches. The expected total efficiency comprises additional peaks, red dashed line, which follow the Fibonacci number system. The proposed approach to synthesize a Fibonacci SCC is based on the properties of the Fibonacci sequence. The initial values of the sequence f1 and f2 are both equal to 1. Now, for I greater than 2, each next Fibonacci number is a sum of the previous two. First 10 Fibonacci numbers are shown in this table. According to Zeckendorf's theorem, any integer number can be represented uniquely as a sum of distinct Fibonacci numbers. Incrementing the index j, we get the largest Fibonacci number fn plus 2 in the leftmost position as shown in this table. The Zeckendorf representations for different numbers n are shown here. Let's now normalize the Zeckendorf representation to the largest Fibonacci number fn plus 2, and introduce an extra value of -1 for aj. Thus, we define sign Fibonacci representation for fractions in the range from 0 to 1. Due to aj taking the extra value of -1, a number of different SFN codes can represent the same fraction. For example, 4/5 has 3 different SFN representations. To spawn different SFN codes, we add 1 to the leftmost one in the Z code. Then we follow both the carries up and subtract 1. This procedure is repeated for all the ones in the original and each new SFN code. As an example, we spawned 3 SFN codes for 3/5 from the Z code 0100. Note that operating a 3 in the second code leads to the overflow, which can be disregarded. Another overflow takes place when 1 is added to A21 in the third code. This overflow is simply added as 1 to A3 and annihilates it. The above spawning rule has 2 important corollaries. One is that for any fraction mn with the resolution n, the minimal number of SFN codes is n plus 1. The other is that for each aj equal to 1 inch SFN code of a given mn, there will be at least one aj equal to -1 in another SFN code. Both the corollaries are demonstrated by these codes. Let's now return to the switched capacitor converters. To realize the conversion ratio equal to a given Mn, we formulate rules for translating the SFN codes to SCC topologies. The flying capacitors in these topologies are always connected in series. So, the coefficient A0 is associated with the input voltage source, while HAJ represents the connection polarity of flying capacitor as detailed here. This example demonstrates how the translation rules are applied to the SFN codes of 3/5. In particular, the second code is translated to this topology. Since A0 is equal to 1, the input voltage source is connected. A1 equal to -1 says us that C1 is charged, while 0 value of A2 means that C2 is disconnected. Due to A3 equal to 1, C3 is discharged. When this forward topology cycle, the converter arrives at the steady state with the output voltage of 3/5 of V in. To find the steady state voltages across all the capacitors, we apply Kirchhoff's voltage law to each topology. This leads to a system of 4 linear equations. The solution of the system is the fractional Fibonacci voltages. Generally, for the resolution n, the number of unknowns will be n+1. While corollary 1 provides us at least n+1 equations. Thus, the number of equations is equal or larger than the number of unknowns, and therefore the system will have a solution. Considering the fact that the above system is solvable, it should also be solvable if V in and V out are interchanged. This means switching the input and output terminals and in fact, turning the step-down SCC into a step-up. It is evident that the step-up Fibonacci target voltage V out equal to 5/3 of V in is reciprocal to its step-down counterpart of 3/5. The experimental setup following the above figure was built around the CMOS bidirectional switches with an on resistance of 1.2 ohm. The rest of the parameters are listed here. The output voltage was measured for 2 different loads and shown in the bottom figure. The blue solid line here is for the load equal to 300 ohm and the red dashed line is for the load of 100 ohm. This figure shows the SCC efficiency measured for the above 2 loads. The blue diamonds here are for the load equal to 300 ohm and the red squares are for the load of 100 ohm. Note that even with the hard load the efficiency does not drop below 90%. Summarizing the above, we have introduced 6 new Fibonacci conversion ratios in addition to the 7 of the binary SCC with 3 flying capacitors. Thus, in this particular case the number of attainable conversion ratios is doubled. This brings me to the conclusions. So, based on the SFN representation, a number of additional Fibonacci target voltages was introduced. This improves the total efficiency in both the cases when the SCC output voltage is kept constant and when it needs to be adjusted to different levels. Another important upshot is that the proposed Fibonacci SCC is compatible with the previously developed binary SCC. Both the SCC can be considered as a computational hardware that solves a system of linear equations. Thank you very much for your attention.